Good morning, everyone. Happy to see so many of you here. I'm glad to be here. Before we start, a little intro about me. So my name is Dirk-jan Mollema. I am from the Netherlands. I've basically been in security for about almost 7 years now. And last year I started my own company where I do a mix of research, consultancy, and also giving training since this year. Given talks at various conferences, Black Hat, DEF CON, etc. And most of my research I actually do by writing tools. So I try to figure out how protocols work, how things all work together. Then I write a tool about it, and I've written several tools on Active Directory and also more on Azure Active Directory the last few years. I have a blog, I have a Twitter account, so if you want to follow my work, then you can do that there. So what we're going to be talking about today is about Azure AD device identities. And it's structured a bit like first explaining what device identities are and why they are important. Then on the technicalities, like how does a device get an identity, how does that flow work, and then we get into all the tokens. So we'll start talking about primary refresh tokens, how these are protected on modern Windows versions, and all the issues that I found in the implementation, and also how Microsoft resolved these issues, and also some scenarios that I found that could be and a different option that you had to abuse this. So just before we start, a little bit on terminology. So this talk is really about Azure Active Directory. So it's not about Azure as a cloud infrastructure provider. It's not about virtual machines, etc. But it's really about the Azure AD identity platform. And the identity platform is for Microsoft 365, also Azure Resource Manager, or basically any other app you want to integrate with it. So this is kind of the follow-up from on-prem Active Directory, but it's really the identity part and not about cloud resources. So all of this is quite important in the whole zero trust architecture, even though it's a bit of a buzzword. If you look at the architectural overview of this, you see that there's some components involved. And of course, on the left top, you see user identities, because this is a very identity-focused security platform. So user identity is very important with multi-factor authentication and other verification means. But you also see device identities. So device identities is what we'll be talking about today, and also how they tie in with this whole security policy enforcement and the whole zero trust strategy, basically. So a device gets an identity when it's either registered or joined to Azure Active Directory, and that can be a large range of devices. So there's different scenarios, some different differences here, but basically you could have a mobile operating system or a desktop operating system that is basically registered or joined to Azure Active Directory. And then the device identity exists as an object in Azure Active Directory. And optionally, you can manage this device by using Intune, which is Microsoft's mobile device management solution, or you can also use some third-party MDM if you want. Now, in Azure AD Security, you have various options to really secure your infrastructure. And if you're looking at kind of the strictest way that you really want to enforce people in your organization to only sign in from trusted devices, then you'll be joining your device to Azure Active Directory. You make sure that it's managed by an MDM such as Intune, and Intune applies all kind of policies to devices. So it manages the settings on the devices, all the configuration of the devices, and by applying the policies and checking if the settings are all correct, the device becomes compliant. And then people use conditional access policies to basically restrict access to resources such as SharePoint to only corporate compliant devices. Of course, in this part, then it's also important to ensure that any device that people use is also really a corporate device. So we're also looking at that they lock down basically the environment by enforcing that you can only enroll devices that are trusted. So they were purchased by the company itself and not just any device that you bought somewhere on eBay, for example. So in Intune, you can set this as enrollment restrictions. And in the scenario that we're researching here, Intune has been configured to block any devices that were not part of the organization. So to give an overview of the research scenario, using Windows 10 here, so Windows 10 or 11, so modern operating systems. Also in the setup, we'll be using Autopilot, which is basically a way to ensure that devices are pre-registered already when you purchase them. So you basically purchase the devices and they automatically become registered in your tenant. And then you know that the device that you purchased is the actual device that's accessing the resource, basically. We're locking down personal devices, so Intune doesn't allow us to just register or join any device. And we require device compliancy with conditional access. And also we have a hardware protection of secrets by using a trusted platform module. So it's basically the most lockdown scenario that you can have. So when I started this, I had a couple of research questions. And first of all, so how are devices actually joined to Azure AD? And how are the secrets that are involved actually protected by hardware? And of course, if we know how it works, then we can also look at if it's possible to extract these secrets anyway, even though they should be hardware protected, and if it's possible to bypass like the device compliancy requirement, because of course, as an attacker, that's quite interesting to know. So let's start by looking at the device join flow. Basically, the device join flow, if you have a device that was pre-registered using Autopilot, then you'll typically set it up by when you install Windows, basically. So it will ask you for your corporate credentials, and then it will attempt to join it to Azure AD. You can also do this after the device was already set up, but basically the flow is similar, just a different way to initiate it. So on this screen, you would sign in with your account. You would do multi-factor authentication to validate that it's really your account. And then in the background, it initiates basically a technical flow. So the device will generate two public-private key pairs. The first one is the device key, and the second one is the transport key. And these are asymmetric cryptographic keys, and a lot of the communication in the protocol, as we'll see later, is based on these cryptographic keys. And the public keys in this instance are sent to Azure AD, and of course the private part of the key that remains on the device itself. So Azure AD can basically validate that the device processes the private key by checking it with the public key that's registered. So when the device registers itself or joins itself, it sends this request. It's just a HTTP post with some JSON in it, so it's not super complex in this case. And just focusing a bit on the components, the first one we see is an authorization header. So this is the header that actually contains the access token for the device registration service. So first the user requests a token by signing in, and then it sends this request to the device registration service to actually register the device. So it authenticates the user doing the registration. It sends a certificate signing request. So basically the device is asking Azure AD, okay, I have these keys. Can you please issue me a certificate that I can use to identify my device later on? It also sends a transport key. And so this is the public part of the transport key. And that's basically a key that's used to provide additional encryption of any communication between Azure AD and the device. It also sends some properties, so it will say that this is the OS version, this is the device type, so obviously this will be different depending on the operating system, and it also shows the host name of the device. Those aren't actually validated, so if you're doing this yourself, you can put here whatever you want. It's just the registration that counts, basically. The join type is in this case 0. So 0 means Azure AD join. There's different values if you're doing an Azure AD join, an Azure AD registration, or a hybrid join, for example. So these are all different numbers. And lastly, there's this device ticket. And basically, we'll get into that later, but it's not strictly required. So if you're registering a new device, you can also leave this out. Now, so it sends this post request. And then it gets a response from Azure AD. Once again, it's relatively simple. It's just a JSON object containing basically the certificate on the top. So this is the signed certificate by Azure AD that the device can use to authenticate itself. And on the bottom, you also see some membership changes. So for those who are familiar with Windows and how it structures local groups, this is the security identifier of the local administrators group. And basically, this is saying, okay, you're now joined to Azure AD. So these users should be local administrator on the device, and it's doing that by passing some security identifiers in there that the device will put in the local administrator group, so that Azure AD accounts that have an administrative role can basically manage the device. So after the device is joined, we can see the status of the device, so that you can do with the dsreg-cmd commandlet, and that basically will show that the device is Azure AD joined. It will also show the device ID, so that's in the middle here. It will show the thumbprint of the certificate. And also something that's interesting is that it says the key provider, so that's where the private key basically is stored of the device certificate. It is the Microsoft Platform Crypto provider, and it also says TPM protected yes. So this basically means, if it shows the platform crypto provider, is that Windows is using the additional security of a trusted platform module to protect this private key, and it's not stored in software somewhere that attackers could extract it. So the idea of a trusted platform module is that it's basically the trusted platform module itself. It has some private cryptographic keys, and if you generate keys inside a TPM, so if you generate private keys there, the key never leaves the TPM except in an encrypted format. So the idea is that even if you, like, as an attacker, has control over the whole operating system, because the private keys are actually stored in the TPM, or they're at least tied to the TPM, then you cannot steal these keys. And basically, if the operating system wants to use the keys, it asks the TPM, hey, I want to perform this key operation. So, for example, it wants to perform some encryption or decryption or signing. It asks the TPM to do that for it, and the TPM basically gives back the result to the operating system. So then even if the operating system itself is compromised, you wouldn't be able to extract these keys because they're TPM protected. And Azure AD uses this quite extensively to protect like sensitive key material. So after the device join, then the user can sign into the device, and basically it signs in using their Azure AD username and password, and then the Cloud AP module in LSS, which is the module responsible for doing the authentication towards Azure AD, issues a primary refresh token. And a primary refresh token is a specific credential that the device can then use for a single sign-on. So let's have a look at the flow there. So the primary refresh token flow starts off by requesting a challenge. So this is quite common in many of these operations. So to prevent basically replay attacks, they always ask for a challenge or a nonce, and the nonce is basically this encrypted string that isn't truly a nonce because you can use it multiple times, but it does expire after like 5 minutes. So if you do a cryptographic operation with this nonce, then 5 minutes later you wouldn't be able to do it anymore because the nonce basically expired. So it first asks for a nonce, and then it sends some signed data to the server. So here we see something that looks a lot like a JSON Web Token, and it is a JSON Web Token. So basically it's sending a request to Azure AD saying, okay, I want to perform this action, and it's sending that as like a signed request. So this token is actually signed with the device certificate so that Azure AD can basically authenticate that it's a real device doing the request. And if we look at the data content, because we can just decode it as it's a normal JSON Web Token, we can see that there's first the request nonce. So it took the request nonce that it received from Azure AD and it put that in that signed data content. And it also puts the grant type as password with the plain username and password in there. So basically, when you authenticate on the Windows login screen on an Azure AD joined device, it just hands over that username and password to Azure AD via this basically signed JSON Web Token. All right, so the reply from Azure AD, if the password is correct, of course, will be this primary refresh token assurance. So it says refresh token, but this is actually the primary refresh token that you get. Now a primary refresh token, it's so the token itself is not super secret because it's sent during various requests. But the thing that makes the primary refresh token very sensitive is especially this session key. So you always need this cryptographic session key to prove that you actually possess this primary refresh token. So the session key here is sent in an encrypted format, encrypted with the transport key, so that only the device itself can decrypt this key and then basically obtain the plain text transport key. We also see that it expires in 2 weeks. It's actually not true. So primary refresh tokens are valid for 90 days, but it still says 2 weeks, and Windows also thinks 2 weeks, but they're in fact valid for 90 days. Now, this storage key or this session key at the bottom, that's the interesting part because you need this to actually use the primary refresh token, which makes it very similar to like a Kerberos ticket granting ticket, because then you also need the session key to use it. And how this all works with the TPM is also quite interesting. So the TPM basically is quite a small chip, so you cannot like store 100 keys in there. But the TPM has basically a root storage key that's stored in hardware. And then any additional keys, such as storage keys that you can use to store encrypted data, they can be stored on disk, but they're always stored in an encrypted format. So the transport key that the device generates is actually a storage key in TPM terms. And when Azure AD issues a session key, it will like encrypt it with the public part of this the transport key. So basically that means that you can only decrypt this key in the TPM, and you cannot use it in the OS. So the OS never gets access to the plaintext session key, but it can only be used by loading this transport key, which is a storage key, in the TPM, and then asking the TPM to do certain operations with the session key. So that's basically how it's like tied to the TPM over these different requests. So just to summarize this, there's the private key of the device certificate, there's the transport key and the session key, and these are all tied to the TPM, and the operating system can use those keys, but it shouldn't have access to like the plain text key material. And the operating system then gets this primary refresh token, and that can be used to perform single sign-on to Azure AD resources. So just looking at like how this PRT is used and what we can do with this from the endpoint. So there's basically quite some attacks that you can do if you are on a system as an attacker that has a primary refresh token. So similar to how single sign-on works in Azure AD, in on-prem AD cases, as a regular user, any process can basically request data for single sign-on purposes. So it can just say, hey, I want to sign into this app. Please give me some single sign-on data. So a regular user can request to use this primary refresh token by asking else as nicely, basically. Of course, if you're administrator or if you're system on the device, then you can also dump the else memory, and you can also steal the primary refresh token in the session key and the session key, but not if it's protected by TPM. So if there's no TPM, then all the things will be stored in software basically, and you can dump the plain key. But if it's stored in a TPM, then you cannot. Even if there is a TPM, then as administrator, of course, you can still like interact with the PRT and the session key, and you can just ask the TPM to basically perform the cryptographic operations for you. So we'll look at that in a bit as well. There's basically two ways that Windows uses PRTs. Maybe more, but there's two ways that I'm aware of. So for native apps, they'll actually ask the web account manager, which is a token broker component. So that handles all the authentication for the apps, and the apps don't need to worry about it. And this token broker basically passes the request on to LSS, and LSS then will ask for tokens using the primary refresh token. There's also a way to do single sign-on in the browser. So then the browser will basically ask LSS for a specific header that it can use when authenticating, which is kind of like a PRT cookie. So it will ask LSS for that cookie, and it will inject that in any authentication flow so that Azure AD can see, okay, this is a device that is that has a PRT, so I can use this for single sign-on. So as attackers, there's multiple ways that we can actually do this. So there's some links here about 2 different approaches, one by me, one by another researcher, about how you can request this single sign-on data if you are running on the operating system as a normal user. And then you can like steal the single sign-on data to perform the sign-on somewhere else. So that's as a limited user. And as an admin, I work together with Benjamin Delphi basically to create a update for Mimikatz that can do this. So here you see that Mimikatz can dump the Cloud AP module in LSS and basically extract the primary refresh token from there. So imagine that we are dumping such a primary refresh token. So now how does the authentication actually look with the primary refresh token? So I already mentioned shortly the PRT cookie. So that's what browsers use to do single sign-on to Azure AD with the PRT. And that's basically a JSON web token. So it will contain a header, a body with some claims, and a signature to prove that it's authentic, basically. And in the header, we see first there's a CTX. That's basically a cryptographic nonce that it uses. There's also the refresh token itself. So this is the primary refresh token that it's using to authenticate. And then there's also the request nonce. So once again, this flow uses this request nonce to prevent basically this from being replayed after the nonce has expired. And of course, we also have the signature. So it basically uses the session key to calculate a signature, and that it's used to sign this JSON web token, and Azure AD can then validate that it was all done correctly. So the technical parts of this signing flow. So this is the simplified version. If it's, imagine that it's a software only key. So the OS basically generates some random bytes. This is called the context, and it uses this for the cryptographic operations. And it puts these random bytes in a key derivation function together with the session key to calculate a derived key. And this derived key, so this will be a different key for each random context that's generated, is actually used together with the primary refresh token, with the nonce from Azure AD, to create this PRT cookie signature. So it basically calculates a new key for every request. So this is the simplified version. Now, if there is a TPM involved, then the flow looks slightly more complicated. So basically, because the session key is not in the operating system, but it's in the TPM, and only the TPM can basically perform crypto operations with it, then the operating system will generate these random bytes. Then it will ask the TPM to do the key derivation. And then the operating system gets this derived key, and that it can combine with the primary refresh token, with the nonce, to create this PRT cookie. Now, there's a bit of an issue with this. So if you look carefully, you see that the only thing that goes to the TPM is basically these random bytes, so the cryptographic context. So if you are an attacker with access to the LSS process, then you can basically perform like a lot of pre-calculation attacks. So if I just give a lot of random bytes to the TPM, it will generate a lot of derived keys for me. And because these derived keys do not expire, they don't have an expiry, they're just based on random bytes basically, then if I have access to the operating system, I can just pre-calculate this and then use these keys whenever I want without even needing the session key. So there's quite a flaw in this. And you can use Mimikatz to do this. So if you load the primary session, the session key basically. So in this case, it's protected by the TPM. Mimikatz will generate a context for you, so these random bytes, and then it will give you a derived key, and that derived key is actually used to calculate the signature. So if we use some tools as part of my Road Tools framework, we can basically authenticate by using this, creating a PRT cookie ourselves, and then providing the PRT context and the derived key that belongs to it, and then basically generate our own cookies at runtime. And basically, whenever we want, we can authenticate using the single sign-on data without actually needing access to the TPM. So the TLDR of this, of course, if there's no TPM at all, then you can just steal the primary refresh token, including the session key as an attacker. If there is a TPM, then you could still acquire combinations of contexts and derived keys that could allow you to use the PRT without actually having access to that device. If you want the longer version of this, it's in my blog here. So there was quite a flaw with this, of course, and Microsoft responded to that by basically changing the behavior of this. So they made some changes in the whole PRT signing flow. They also changed the storage mechanism, which broke the Cloud AP functionality in Mimikatz for a while. Nowadays it's working again, so you can dump the PRT again in Mimikatz, but you cannot do like the new version of the key derivation function. So if you find blogs about this, like explaining how to do this, then some of them may be outdated and not work anymore. And basically in the updated PRT structure, we see this added field which says KDF version 2. So that uses a new key derivation function to basically calculate these derived keys. And if we look in the documentation, then they basically changed it so that they don't just put like these random bytes called the context to derive the signing key, but they actually use a SHA-256 hash of that context plus the body of the JSON Web Token to calculate this derived key. This is documented. I actually only found out it was documented after I reverse engineered it all, so could have saved myself some issues here by reading the documentation. But basically, if we update this graph, then now it first takes the nonce from Azure AD, so that's something that expires after a few minutes. It combines that with the primary refresh token, and it uses that to create the JSON Web Token body. Then it combines that with these random bytes, and then it takes the SHA-256 hash of this whole thing, and that's called the KDF context. And the KDF context, that is actually used in the key derivation with the TPM to get this derived key. So you see that because it now includes this nonce, which is time bound, so it only works for a few minutes, then you can no longer do this pre-calculation and like pre-calculate these derived keys to use at a later point, because you will always need to have a recent nonce, and the nonces are controlled by Microsoft, so you cannot create those yourself, basically. So this was patched with this CVE number, and basically the new method prevents you from pre-calculating these derived keys by putting the nonce as part of the key derivation function. And they also prevented you from downgrading the key derivation function. So I assume it's stored somewhere in the PRT which key derivation function was used when issuing it, so that you cannot like simply remove the header and then use the old calculation. So this is fixed quite well. So some other scenarios, like there's more stuff we can do. So of course there's some downsides to what we've discussed previously. First, you need to be admin on the device. You need to dump LSS, and dumping LSS is something that a lot of EDRs are very interested in. So it's quite noisy if you're doing it as an attacker. If it's stored in the TPM, if it's modern security protected, then you can no longer steal it. You can also no longer pre-calculate these things. And of course, if the device is disabled, then any primary refresh tokens from that device are also disabled. So I wanted to come up with a new way to do this. And basically, it combines some knowledge of the two previous parts. So I looked at, because we know how the device registration flow works, we can basically emulate that ourselves, and we know how to get our own primary refresh token, and we know how to get access tokens for the user by using single sign-on. So I thought, okay, so if I can get a single sign-on token from the user session, can I also get a single sign-on token for the device registration service? And it turned out that's possible. So you can first initialize this single sign-on flow. And that's basically done with a small tool that's called row token. So you give it the nonce from Azure AD, and then it will like calculate this XMS refresh token credential, which is the signed primary refresh token that browsers use. And then you can get a token for the device registration service with RoadTX, which is a tool I wrote to exchange tokens, basically. So you see it as a token for the DRS. So DRS stands for Device Registration Service. So it asks a token for the device registration service, and it uses this PRT cookie to authenticate the request. And this will give you an access token that can be used to register devices. And then you can register the device. So this is an older proof of concept that I wrote. Nowadays, this is all in RoadTX, but basically this performs the device registration flow, and you see the result here that it contains the certificate of the device and also the SIDs. And basically, this gives us a device certificate with private keys that we control because we generated them on the fly. And this certificate can be used to pretend that we are a real device towards Azure AD. Now, once we have this, we can get a primary refresh token. And for that, because it emulates the flow on the sign-in screen, we only basically need the password. So we send the user's password to Azure AD, and we get back a primary refresh token. We authenticate the request by using the device. And then we get back a primary refresh token and the session key that also belongs to the primary refresh token. So this is no longer protected by any TPMs, but we now have this on disk basically. So we can use this PRT and this session key to sign in. So this is just to get a access token. There's also features in RoadTX that allow you to use this in an interactive flow in a browser. But basically, we authenticate with this PRT. And if we look at the token, then we see that we got an access token, which not only contains the password claim, but also the MFA claim. So that's quite an interesting scenario because we never did any MFA for this user, but because we registered basically the device with a token that already included an MFA claim, because the token originated from a device on which MFA was done, then the tokens we get after with our registered PRT also contain an MFA claim. So this is basically a way to extract these tokens and to steal tokens with an MFA claim without ever doing MFA for the user. So to summarize this, we can request single sign-on tokens from a user session without any admin privileges. These access tokens contain an MFA claim. If you use this to register a device, then any PRTs you request with that device that belong to the same user also inherit this MFA claim. And you only need the passwords to get a PRT. If you have ADFS, you could probably also do this only using single sign-on, but that's not something I've researched. So basically, this is a free MFA upgrade from your token because we only use the password to actually get the PRT. So this also has some upsides and downsides. So because we registered a new device, it's basically a separate device. It's not a real device. But if the old device is disabled, then the PRT from our new device will still work. Of course, the downside is that this requires permissions to register devices or join devices, which is not always allowed. You can lock that down in Azure AD. And this also doesn't mean that the device will be allowed to enroll in Intune, because we registered a new device, which is not known as a corporate device. And if we need to access anything that's protected by conditional access to only allow compliant devices, then basically it will not work. So this doesn't cover our full scenario goals. So for the last step, looking at bypassing Intune restrictions. And basically this is another dive in how these Intune things work. So something to consider is when you enroll a device in MDM, that's actually a different process from registering the device itself. So if you look at this from a user perspective, they only enter their credentials once, and then the device will first register itself and then enroll itself in MDM. But that's not how it works under the hood. So it's two different registration requests. And even if you block non-corporate devices in Intune, you could still register or join the device in Azure AD because this is something that's separately controlled. If you do this in Windows, then if Windows sees an error, so if it sees it's not allowed to enroll the device in Intune, then it will automatically roll back the Azure AD registration as well. But if you do it yourself, you can just do those separately, and you can still like register or join a device even if you're not allowed to enroll it in Intune. Of course, this doesn't really gain you anything, because the goal of the goal of this was to bypass like conditional access policy to require a compliant device state, and you only get that by enrolling it in Intune. So by just joining the device, we cannot meet this this compliancy. So some more digging into this. There's a few interesting parts here. So if you're using Autopilot, then basically the devices are already registered in your tenant based on their hardware properties. And if you wipe those devices and register them again, then it will reuse like the same device ID in Azure AD. So my question was like, so how does Azure AD actually know that this is the same device? Like if I wipe this laptop and I register it again, it will use the same device, it will override the same device, and it will know that this was like a pre-registered device. So that's the part that comes into play, is this registration request again, and especially this part on the bottom. So this is actually a device ticket that proves to Azure AD like which device it is. So of course I was wondering, okay, how is this structured and where does it get that? So how does it do that? And also, like if you reused the same parameter, it will always override the device. So this is apparently something that is really tied to the device, and it knows the device hardware based on this ticket. It does seem to expire after a certain period of time. So it's not something that's like fixed or something. So it is some device tickets for your device, but it's not related to Azure AD basically. So I did some reversing of this. Which was quite annoying because the registration flow is a web-based app. It uses the WinRT framework, and it also calls WinRT APIs, which means that it's doing some inter-process communication. So it actually spawns a different process to do the registration than the one that does the app. But eventually there will be a DLL host .exe that it spawns with the DLL in there that contains the registration logic. So once I found that out, I just looked into reversing this, and I basically found like this string. So it's probably a bit small to read, but you can see that it's like instantiates a class of the Windows Security Authentication Online ID Service Tickets request. I was like, okay, what is this? I've never heard of this, but it's documented. So the Online ID Service Ticket request, basically to sign in a user or device to the live endpoint. So that's like what you use for Microsoft accounts. So apparently your device has its own Microsoft account that it uses separately from any Azure AD or Intune registrations, and it uses like these APIs to ask tickets for that account. So your device has its own Microsoft account. This is also what it uses for licensing checks and such. And when device-specific authentication is needed, so it's when it does the device identity authentication, then it uses these tickets to prove its identity. These tickets are cached in the registry, actually in the current user registry hive. So any tickets that were used in your user session, you can query from here. They are DPAPI protected, but the protection is tied to the machine, so any user on the machine can decrypt them. And basically you can just enumerate these using PowerShell. So by enumerating these keys and then basically decrypting them, we find this token. So here we see also the token scope is the enterprise registration.windows.net. So it's a device ticket for the device registration. Now, of course, these cache tickets are nice, but like I said, they expire after a certain time. So if the device registration was done a long time ago, then these cache tickets are a bit useless. So I did some more reversing and found the exact WinRT API calls that were needed. So there's this endpoint involved that it asks the ticket for, and there's the app GUID that's used for registration. And basically, when you know all these parameters, you can write a very simple .NET program, which basically creates such an online ID system authenticator request. and it asks a ticket for the enterprise registration.windows.net. It sets the app ID to the same ID that Windows uses, basically. And then it requests this ticket from the system, and it prints it to the console. So if we compile this and we do this, then basically we get this device ticket that contains the device identity. And with this ticket, if we actually do the registration again, but now provide this device ticket, then we will actually override the old device. So if you use the RoTX device module and you specify the device ticket that we obtained from the Windows host, basically, then it will override this old device, and now we have a device that we control which has the same ID, but we have the keys actually stored on disk instead of them being TPM protected. So you also see that, like here, I registered the device, and you see the device ID is the same device ID than what Windows reports on the old device. So you can just request like a device ticket from a low privilege session and then override the old device. And the nice part is that the device basically retained the original properties. So before they basically changed this, then it used to be that even if you overrode the device, it was still considered compliant, and any sign-ins you did using the stolen device identity would also be considered compliant. So that's, you could steal that, and basically the original device was no longer like working properly, but you have the device as an attacker, and the Azure AD still considers any tokens issued to that device like compliant. So just to summarize this, any user that had a session on this device could request this device ticket, which could be used to override the device. If it was pre-registered using Autopilot, then it will do this hardware matching and actually override the device based on the ticket. It overrides the device in Azure AD using, of course, our own cryptographic keys. So if we request any tickets after that, then we can just decrypt the session key using our own transport key instead of it being tied to a TPM. So in this case, you don't need to steal any PRTs from LSS. You don't need to worry about TPMs. And actually, you don't need any administrative privileges at all, because you can just request this from a normal user session. Some bonus features. So you could use any identity to override the device. It didn't necessarily have to be the original user that was using the device. The device ticket also stays valid after wiping the device. So if I steal the device ticket, I wipe the device because it was compromised, for example, then I could still use that device ticket somewhere else. And if you use a new account to override the device, it became the new device owner. So then it can actually recover the BitLocker keys that are stored in the device, because by default, users can read BitLocker keys for devices that they own. So if the BitLocker keys are stored in Azure AD, then you could read this after you overrode the device. And also the nice part is that the original device still kept its link to Intune. So, like I said, the registration in Azure AD and Intune is separate. So if you overrode the Azure AD part, the device would still be talking to Intune and it would still report its compliancy. And basically, Intune would keep reporting the device as compliant to Azure AD, even though the device was no longer the original one, but was now one controlled by the attacker. And the device retained its compliancy status. So just to the complete chain, you could do a few commands in a low privilege session of the victim. You could request a single sign-on token to register a new device. You could request a device ticket to override the legitimate compliant device. And then you could gain access to the primary refresh tokens for the victim user. You could have an MFA claim also included in that. You could have the compliant device claim from Intune. And basically this way you could comply with very strict conditional access policies. This bypassed the need to do MFA for your victim user, bypassed the TPM protection of secrets, and it also bypasses the need to dump LSS or have administrative privileges at all, because this could all be done from a user without any administrative privileges. So I reported this all to Microsoft actually already quite a while ago. So they fixed the overwriting a device or registering a device using single sign-on. They fixed it in September 21. And also they already made some other fixes for to cover some scenarios. So they did basically in a phased rollout. And nowadays you cannot use any tokens that originate from single sign-on to register new devices anymore. Now the overwriting a device via a device ticket, that was something I reported in May 2021. So it's also quite a while ago. They patched this a year later, so it took them a while to actually fix this. And it actually took them even longer to enforce this server side. So they actually rolled out the final enforcements that prevent you from like overwriting a device and getting it compliant in February. Or at least so I thought. So this is actually the fun part of this. So actually I was making some screenshots for the presentation earlier this week, and I found out that actually the device overriding still worked. So they said it was fixed, but it wasn't. And then there was some conversations with Microsoft involved. So they actually rolled out the final fixes for this yesterday. And it's still a bit of a question, like if this is fully fixed. So basically what they did, the device registration method, that's unchanged. So that's not something they changed. You can still override the device using the device ticket, but it does remove the compliancy status. And so it's not immediately compliant anymore. But when I was playing with this, I found out that like after the original device synced back in Intune, then Intune would happily write back like the compliancy status to the new device. So you could still kind of get it compliant. So this is what they fixed like yesterday night. So I was actually chatting with them until 1 a.m. to confirm that whether this was fixed or not. And now so now they basically disconnect the device in Intune with the device in Azure AD when you override the device in Azure AD. So it doesn't get the compliancy claim anymore, but you can still like override the original device. So I'm not sure if I would consider this 100% fixed, but at least it's no longer possible to like get that compliancy claim by just overwriting a device that's already compliant. So to conclude, so the secrets in hardware were not very efficiently protected. Basically, you could just pre-calculate whatever you needed without needing to dump anything from the TPM. You could obtain a PRT by simply registering a device. A low privilege user on the device could take over the device identity, and you could all do that using some single sign-on magic. So this should be all fixed if you patch your endpoints. And of course, the cloud is already patched for you. Doesn't mean that there's no bypasses for this. So I have some new research that basically defeats the whole TPM protection again. But that's something for another time. If you want to play with this yourself, like everything, all the tools I've showed here, they're open source. So they're part of the RoTools framework, and you can play with devices and tokens using RoTX. I also have some RoTools stickers for those of you who are interested. And if there's any further questions, feel free to ask them now, ask them later via Twitter or mail. And well, thanks for your attention.
Okay, so if there is any question, please raise your hand so I can bring you the microphone. Okay.
Thank you for your talk. My question is more about the enrollment process of a device to the identity platform.
Mm-hmm.
You said there are two types of keys generated, one for the device, it was called device key, and the other one was the transport key that are generated with a TPM and are stored there.
Yes.
In your research, have you looked on how those keys are protected by the TPM? Because from what I know, you can use the TPM as a normal user, you can generate keys, blah, blah, blah. But if they are not protected by certain policies that restrict access to the keys, you should be able to access them. do you have some insights on how Microsoft protects this kind of keys with a TPM, or was out of the scope of your research?
So it was not part of this specific research, but I did some research into the crypto internals last year. So basically there's different levels of protection. So Microsoft uses some layers below the TPM to provide software access, and basically they store parts of the parts on disk, and parts are stored like protected with the TPM. The keys are always restricted to system only, so a normal user cannot load the keys. They cannot use the keys because they have access controls on them, which only allow system to use them. And also like the transport key, it's a storage key from the TPM. So you can only perform certain operations with it. So you cannot say like, okay, I want to use this storage key to like decrypt this encrypted session key. But you can only like derive new keys from it. So those are restrictions imposed by the TPM on it. And what I found, they implemented that quite well.
Another thing is that I know Azure has an identity system for embedded devices. Have you considered also looking in the embedded environment and the identity part that goes there?
I have not, no.
Because things get a little complicated with identity when you don't have users, and I find this field of research quite interesting. How do you protect your keys when you don't have a user?
Yeah, so there's also like autopilot enrollment scenarios in which the device enrolls itself based on some TPM attestation. I also have to look into that still because, well, it's a different flow. This was a user-driven registration, so you always need a user account to register it. Exactly. But there's also ways that devices can enroll themselves, but I've not looked at that yet.
Okay, thank you very much.
Any other question? Yeah.
Okay. Great talk. I would like to ask you, because you use the same device ID to override the device in the Azure AD. Well, at the same time, I assume you regenerate the transport key, the session key, stuff like that. Mm-hmm. What happens to the old device? Because it assumed, based on what you said, it overrode once again to add the compliance to the Intune. So shouldn't the session key and the transport key from the old device be revoked on the server side, but it wasn't, or something like that?
Yeah, so like once you have a primary refresh token that has its own session key and that you can use irrespective of the device identity. So if I override a device key, then the original device can no longer request like new primary refresh tokens, but any old ones still work. So it cannot use its device identity anymore because the certificate is not valid anymore. It doesn't match anymore with the one that's registered in Azure AD. But primary refresh tokens, they still work.
Okay, thank you.
Any other question?
I would like to go back to the TPMs. There is a trusted root system where the TPM should attestate the state of the device. Isn't that tied into the onboarding of the device?
So they use some attestation in the Intune registration, but not in the Azure AD registration. So there's no need to prove to Azure AD that your keys are in the TPM or not. Azure AD doesn't actually care or show you if the keys are in the TPM. So if I am an administrator and I look at the list of the devices, there's no way from Azure AD to see like, oh, those keys are in the TPM or those are not. It uses a different format to register them, but Azure AD doesn't care like if you use a software key or a TPM key. It doesn't enforce you to do anything. You can enforce that there should be a TPM with Intune, but that's separate from the device registration. So they don't require you to prove that keys are in a TPM or offer you a way to only allow devices that have a TPM to actually register or join.
All right. Thank you very much. We are kind of running short in time, so I think we can move on to the next speaker. Charlie?